All right, everybody. Well, welcome. So, welcome to the September. It's September already. Can you believe it? The September meeting of the Grand Strand Astronomers. So it's hard to believe we're already into the school year and only have a few months left in 2024. So, a couple things before we get started, if Patrick doesn't mind. Did anybody catch the lunar, the all admittedly small lunar eclipse the other night?
I saw it for a while.
Yeah, I did not. I was unable to get out. So yeah, I don't think it had covered very much is covered up here. So maybe next time we'll do a little bit better. I just kind of want to remind everybody of a few things here. Um, the next observing session is October 5th, Saturday, October 5th, at Hampton Historic Site. If you haven't been out there, I highly recommend you do get out there. We were out there here August 31st, which was our last observing session. That's the September observing session was August 31st because of that was the best new moon. And it was actually a really great night, although transparency was slightly off. The seeing was excellent, but in the south, it looked fantastic. And in fact, it is we were all talking, Gerald and I, and we were all talking about the fact that um, that was the best view of the Milky Way we've ever had out at Hampton. So you could actually, you could really start making out some details in the Milky Way in the south, right? Because that looks out over the Francis Marion National Forest. It was amazingly clear, especially early in the night, amazingly before the fog set in around midnight ish. But it was actually really great. So if you haven't been out there, it's definitely worth getting out there. So next observing session will be October 5th. I think Gerald Drake, who couldn't make it today because he's traveling, will be running that session and let everybody know, of course, the day of the event, if it's going to go or not, depending on the forecast, right? But October is usually traditionally pretty good. Of course, our next meeting will be October 24th. I'll let everybody know what our program is for that. Um, as I mentioned before, I think we went live. I still want to thank Tim for all his work on the newsletter. Our latest newsletter is out. You can access it on the website. It's always got the latest newsletter, as well as an archive of all the previous newsletters. You have all the history. So, and certainly I want to definitely put a plug in for Tim in terms of anybody that wants to submit an article, please send it to Tim. You don't have to worry about any formatting or anything. Tim's the expert. It can just be an email talking about either a piece of equipment you have, something you saw, something you read about. If you have an interesting website or an interesting uh, tip or technique you've seen somewhere, let Tim know and we can craft an article out of it. So the other thing is I wanted to just bring up to the group, and I'll put it out in an email. Do we want to do a public observing at Merle's Inlet down here in Merle's Inlet? I was talking to Huntington this summer, and they were interested in maybe trying to arrange something this fall. So if people are interested in doing a public observing there, I'll start a discussion on the email group. Okay, so that's pretty much all the business stuff I had. So without further ado, since you're probably tired of hearing me talk, I'll introduce Dr. Patrick Treuthart, who's on the call. He's an astrophysicist with the North Carolina Museum of Natural Sciences Astronomy and Astrophysics Laboratory, the lab that needs a shorter name. Yeah.
Exactly.
And so I'll let him introduce himself, and we'll hand the show over to him.
All right. Well, thanks, Ian, and thanks for inviting me, and thanks for having me come talk to you guys. So let me share my screen. All right. Yeah. So I'm Patrick Treuthart. I'm one of the two astronomers at the North Carolina Museum of Natural Sciences in Raleigh. I believe I've spoken to your group once before, at least once before. So I don't remember faces, so don't know if I've seen you guys before. Um, but yeah, so I study galaxies. I'm interested in galaxy morphology and dynamics, which means I'm interested in the shapes of galaxies and the underlying physical properties that create those shapes that we see. Um, but what I want to do is I actually thought we'd talk about some papers that came out like at the beginning of 2000. Um, and so it was the first kind of concepts of uh, basically what we're going to be talking about, which is a galactic habitable zone. So like where in the Milky Way should we where in the Milky Way would life be most probable, and where should we actually be looking for life? So we've people have heard of like a stellar, a circumstellar habitable zone, or a habitable zone around a star. And so people in the early 2000s started thinking about, is there a region in the Milky Way that's more conducive to the emergence of life than perhaps other regions of the Milky Way? So that's why I titled this talk, "Where Should We Look for Life in the Milky Way?" So it's a little tangential to what I work on. Um, so there's a little bit of dynamics in here, but not much. But this is mostly kind of a review of some papers that I've read. Um, but again, this is not going to be comprehensive. This is not going to be in like full detail. This is just going to be like the first concepts that came out in 2000. Now, since like 2001, 2004, when these first papers came out, like progress has been made, and we are no closer to coming up with an answer. But I just want to give you kind of the first hypothesis, the first like thoughts of what we should be thinking about when we talk about looking for life in the Milky Way and on a broad scale. Um, all right, so let's talk about the Milky Way. So this being an astronomy group, I'm sure everybody has seen the Milky Way. And this is I like showing this video whenever I talk about the Milky Way, just because it's an interesting perspective that many people don't see, where the telescope is actually fixed to the rotation of the Earth. And so you actually get a sense that the Earth is moving through space, and all these faraway objects are just not moving at all, that we're actually the ones moving. So it's a nice perspective. But you can see the Milky Way, that the hazy band in the sky there. I'm sure you're all pretty familiar with that. Um, and so if we take a closer look at the Milky Way, so if we eliminate the horizon, and we basically get a 360-degree view of the Milky Way, this is what it looks like. And if you pay attention, so if you actually go out into like a really dark area where there's good seeing, like it's just, pristine conditions, you can actually see a lot of this detail, which maybe you have, maybe you haven't seen before in your life. Um, Actually, the first time I've ever seen a lot of this detail was when I went to a conference in Hawaii. And I went to the Big Island and I stayed in an Airbnb that was like in a subdivision with not a lot of lights. And yeah, and I could actually see the color of the Milky Way, which I had never seen before in my life. And that was just amazing to actually be able to see that with your own eyes. And so like in this image that you see here, if you look toward the center there, you see it does look kind of yellowish orange. And as you move away toward the edges of the photo, you can see that the band actually becomes a little bit more blue, or a little bit more blue. And that's real. That's actually stars essentially of different colors, um, creating that color difference that you can see there. And you can see in the center, it's a little more bulbous in the center. That's the bulge of the galaxy. And then the thinner parts toward the edges of the picture, that's the rest of the disk of the galaxy. So obviously we live in a disk-shaped galaxy. We don't live in an elliptical galaxy that looks more like a spheroid. Um, but what you're seeing in here is essentially you're seeing a color difference. So you're seeing different types of stars. You're seeing dust, which is obscuring the starlight. So that's all those dark bands that are cutting through the plane there of that hazy band. You might be able to see a little bit of gas, so some of the pinkish hues. Um, and you definitely see stars. So everything that's emitting light here, everything that's emitting kind of blue, white, or yellow light, that's all stars, both old and new. So what you're seeing here is essentially 200 billion stars, uh, within our own galaxy. And so we've taken images of small sections of sky, exposed. We've done this with the Hubble Space Telescope, where we've taken a a deep image of a small section of sky, and we've basically found 10 to 12,000 galaxies in that small section of sky. And if we extrapolate that out, we now think that there are 10 times as many galaxies in the observable universe as there are stars within our own galaxy. So we estimate there are about 2 trillion galaxies within our own universe. And most of them are spiral galaxies like the Milky Way. Okay, so when you're looking at this photograph, there are actually components to the galaxy. So we can actually break the Milky Way up into different components. And these components, it's hard to see. I mean, you really won't be able to see most of these with the naked eye. You need basically kind of research grade equipment to really parse these apart. But this is a little diagram I built. Oops, yeah, that's the wrong color. Hold on, let me see. There we go. We go back here. Okay, there we go. Not supposed to be that bright red. But yeah, so what you're seeing here, so what I've done here is I've basically pulled apart the galaxy and kind of made a diagram of what you're actually seeing. So where we live, the main part of the galaxy that you see in these photographs, that's the thin disk of the galaxy. That's where a lot of the bright stars live, the young stars. And it's also where you get all the gas and a lot of the dust. It's all within this thin disk of the galaxy. The thin disk basically is about 100,000 light years across from edge to edge, so 100,000 light years in diameter. And it's only about 1,000 light years thick. So if you basically, it's essentially the same as a CD. So if you imagine the diameter of a CD to the thickness of a CD, that's essentially the same scale as the thin disk of the galaxy. So it's a very, very thin object. And so we have the bulge in the middle, that's the orange sphere. That's composed of stars, mostly older stars. And the reason why it becomes like the spherical-like object is because those stars are actually in random orbits. So they're not in planar kind of circular orbits, they're actually being scattered in every direction. So that's why you get kind of that puffed up spherical-looking object. And so that's about 13,000 light years across. And then we have the thick disk, which kind of surrounds the thin disk. Um,
Oh, oh. I think we have Houston, we have a problem. I don't know if you can still see us, Patrick, but we can't hear you. I think
I can see him.
yeah, but he looks frozen. He's pretty good at being still, but not that good. Yeah, that's what I thought. I just pulled out my phone since he has my mobile number. Well, everyone, well, so we take this break.
While we're waiting for him, I got a question. Maybe you can
Sure.
answer. The bulge in the disk, is that the old stars being pulled in because of the rotation?
Well, the bulge in the disk um, are older stars, right? Um, in terms of they're the older stars, right?
Okay.
So they have more, their orbits are a little more randomized, right? Like the bulge is very old stars, so it's the orbits are like completely random. Uh, the the thin disk is where most of the gas and dust is, which is where all the new stars are born. That's probably a
Okay.
good question for Patrick. I assume he can rejoin because he hasn't texted me and messaged me. Um, So to say like, oh, my power's gone. He has gigabit Ethernet at his house, so usually bandwidth's not a problem. Yeah, different components inside the galaxy. They're different components. But again, most of the dust is in the thin disk, and that's why that's where a lot of star formation goes on. It goes to the arms, and the arms are sort of like traffic pileup. The best way I usually describe it to my students is it's like if you were to go above, like if you're driving on 501, like maybe at noon, there's places it really knots up, right? You have to wait, and then there's places you can kind of really go, right? That's sort of the same thing. Like if you were to go up in a traffic helicopter, and I don't know why I'm so fuzzy on the screen, but I don't feel that fuzzy. Maybe I didn't get enough sleep last night. But if you were to go up in a traffic helicopter and look at it, you'd see like groups of traffic, right?
Yeah.
You wouldn't see necessarily the individual cars going in and out. That's sort of what the spiral arms are. So there are areas, and when the gas and dust goes through there, it gets compressed or it gets upset, and it can collapse and form stars. In fact, if you look at the leading edge of the arms, there's lots of bright blue stars. But by the time that they rotate through to near the end of the arm, a lot of the very hot stars have very short lives. They're gone. It's more reddish stars coming out the back end. So,
Okay. Interesting stuff.
Well, sorry about that.
the last words you heard were thick disk.
Oh man. All right. Well, sorry about that. For some reason, my computer totally crashed. Everything just froze. Yeah, I apologize.
So Tim, it's good you can ask your question and actually get a real answer.
Yeah, I was questioning about the bulge in the middle there. That's you mentioned it's old stars.
Yeah.
As the universe, as the spiral spins, does it suck the old stars into the middle, or is the spiral throwing stars out? What, I mean, is it like a hurricane? I mean, how does it work?
Yeah, so it's it's not quite like a hurricane. So yeah, so these components so they're connected dynamically, but there's like weird things that go on. So there's a lot of like orbital dynamics that go on. So let me okay, so we stopped at the thin disk or the thick disk, right? So let me show you the photos here. Hold on. Um, yeah, let's try this again. Okay. Yeah, so you can have stars kind of migrate in their orbits like inward and outward. But generally stars kind of stay within their zones. Um, uh, I mean, I'll show you a better diagram later on.
Okay.
But if we look at okay, so these are the components of the galaxy. But if we look at the next image, so this is an artist conception of what we think our Milky Way looks like. So obviously we can't go outside the Milky Way because it's so big, but we can be creative and kind of look through the Milky Way and kind of determine where structure is to kind of understand what it looks like where we are and where we are in it. So if you can see my mouse pointer, I don't know if you can you see it?
No.
No. Oh, okay. Well, if you look toward the
There it is.
oh, you do see it? Okay. So down here is where the sun is, and right here is the center of the galaxy. And so, okay. And so right here is a bar structure. This is a linear structure running through the bulge of the galaxy. And so the bar actually, because it's a linear structure with a lot of mass in it, it actually kind of redistributes, it kind of imparts a torque within all of the orbital structure of everything in the galaxy. And it imparts like a large torque because this bar is also rotating. And as it does that, it kind of takes away from and imparts upon, like it gives angular momentum to these objects. And so by doing to these gas clouds or stars and things like that, and by doing so, it causes them to either move outward or move inward. But they only go so far. They only go to these like basically regions in the disk where basically the forces are now balanced. So by doing that, then you end up with these regions called rings. So if you ever look at well, so the best example is a galaxy called NGC 1433. And this galaxy has just every single resonance structure you can think of. So it has all kinds of rings. It has a nuclear ring, an inner ring, an outer ring. And basically what's happening is all of the gas clouds and the stars have kind of been redistributed throughout the disk and kind of forced into these ring-like structures. So it's no longer like, if you can kind of think of it as just like a homogeneous disk, it's now all the stars and the gas clouds and things like that are basically all kind of forced into these resonant structures, and they're orbiting around in these resonant regions, and it creates these ring structures. But you still end up with a bulge, you still end up with the bar, things like that. So not everything is kind of destroyed, but things are rearranged. So the stars in the bar, because they are kind of in these random orbits, they're not really going to be affected as much by like these torques, for instance. So I don't know if maybe that was a little bit too much. I don't know if that really totally
Yeah.
answers your question, but yeah.
Yeah.
But basically, yeah, the bulk like these things kind of want to stay where they are more or less, but they do migrate a little bit. Yeah. Okay, so right, so the galaxy has these different components. There's a so I can't let me just backtrack for 1 second. Um, so there's the bulge, the thin disk, the thick disk, and the stellar halo. The stellar halo encompasses basically the entire galaxy. It's about 650,000 light years across. The thin disk is about 100,000 light years across. The thin disk is about 1,000 light years thick. The thick disk is about 2,000 light years thick. The bulge is pretty big. Um, but yeah, so again, so the Milky Way is about 100,000 light years across. And so what that means is that like there are a lot of stars and the Milky Way is huge. So if we want to look for life in the Milky Way, we almost need a targeted approach, because hypothetically looking at 200 billion stars, you know, in a you know in a galaxy that's 100,000 light years across, I mean that takes a lot of time and a lot of effort, for instance. So we kind of want to have a targeted approach to this. And so to give you a sense of like how let's scale, um, I don't know if you've ever seen these videos before by James O'Donoghue, but these are fantastic. But this kind of gives you a sense of scale. So what you're looking at here is a scale model of the Earth-Moon system. And so the Earth and the Moon are the correct size and the correct distance from each other. And then now he just included a pulse of light, a light pulse in here. And what you're seeing is the light travel time between the two objects at the correct scale. And so it takes about 1.25 seconds for a light pulse to travel from the Earth to the Moon. So it takes about 2.5 seconds for basically a round trip for the round trip travel for a beam of light, for a pulse of light to leave the Earth, bounce off the Moon, and come back. So the distance, and that's the nearest object to the Earth. So that's the Moon. So now, if we think about the Sun, the light travel time from the Sun to the Earth is about 8 minutes, right? So really, the round trip travel time is about 16.5 minutes. So a beam of light traveling from the Sun to the Earth and then reflecting back to the Sun takes about 16 minutes of travel time. And so that's the nearest star to us. The nearest star is about 8 light minutes away from us. And so I'm not going to show you this entire video, but you can see that the light beam is just crawling across in this scale model. And this is scaled in distance. The sizes of the objects are just inflated so you can actually see them. Okay, and so here's a scale model of the solar system. Again, the sizes are just greatly inflated, but the distances are correct. But now if we talk about, well, what if we actually could travel faster than light? Like how long would it take for us to like travel to, for instance, Pluto from the sun or even to the next nearest star? Well, if we if we use the Enterprise, for instance, if we go at warp 9.9, it still takes about 18 hours to get to the next nearest star. And that's essentially as fast as the Enterprise is going to go is 9.9. And so what that means is, and the next nearest star is Proxima Centauri, and that's about 4.2 light years away. So even traveling at warp 9.9 in Star Trek lingo, I mean, it still takes 18 hours to get there, and that's traveling, almost 10 times the speed of light. So in no way are we ever going to be able to effectively talk to anybody, because even if there is even if there is life on a planet orbiting around Proxima Centauri, if we send a signal to them or they send a signal to us, it would take 4 years for the other party to get that signal. And so like communication back and forth would lag by 4 years in each direction. So it would be an 8-year round trip between signals. So it's direct communication with any kind of life form is going to be tricky. Um, all right. So what should we look for? And so what my talk is based on is looking for looking for complex terrestrial and Earth-like life. Okay, and so we got to narrow. So basically, we have to narrow things down. So we want to look for things that are complex, uh, because that means that it has had time to evolve and develop. So things had to have been stable for a long period of time for these beings. We want terrestrial because that adds a level of complexity to the life forms. So, for instance, like here on Earth, the the terrestrial life forms.
Oh my goodness. Well, you know what? I think we have another crash.
Fantastic.
Yeah, that's quite the picture from the golden age of science fiction, huh?
Yeah, it's got Isaac. Oops.
And just like that, he was gone,
Warp speed.
and we didn't get a chance to thank him. All right, so I think the verdict's in on the latest version of Ubuntu 24.04.1. I think it still needs a little bit of work. Well, we'll just wait. I'm sure he'll be right back. Time to reboot and rejoin. Yeah, these concepts, I find these concepts really interesting about, trying to explore where life would be most possible, where to sort of, where we'd most likely find life in the galaxy or in not just in our galaxy, in any galaxy, all right?
But don't they have a way to disseminate which stars are kind of like our sun, find that Goldilocks distance from the sun?
That's that's a component, is the right distance from the host star. It doesn't have to be like our sun, because it turns out a lot of planets, a lot of type stars have planets. But you need to, well, there we go. We need the right distance to indicate that they have water.
Oh, yeah.
But that now what Patrick's talking about is they're sort of looking a little beyond that, right?
Okay.
Sorry, folks. I apologize for that. This is basically running off of Keynote online, and I think my computer's having trouble doing both Zoom and Keynote online at the same time. Uh,
Starting a slideshow.
all right. Slowly thinking. All right. Did we make it through this slide? The complex terrestrial Earth-based Earth-like life?
I believe so.
Okay. All right. Right. Okay. So basically, what we're doing is we're narrowing things down. Uh, we're making it we're making things as focused as we can. So we're just not like looking for everything. We're looking for things that could survive a long period of time, evolve, and potentially be something that we can communicate with. Um, all right. You may be familiar with like the circumstellar habitable zone, which is basically just the region around a star where the temperature, so basically if a terrestrial planet is orbiting around this star at a specific distance, the temperature is good enough so that way you don't end up with ice or vaporized water, where you can actually have liquid water on the surface. This is what's known as the Goldilocks zone. So with hotter stars, that zone is much further away from the star. With colder stars, that zone is closer to the star, and sun-like stars, it's at some middle distance. And so the Earth actually orbits around the sun within that Goldilocks zone, within that habitable zone of the sun, where you can have liquid water on the surface. So the question is, does the galaxy have some kind of habitable zone within it as well? And so what would be the constraints where we could have that zone? And so these papers from 2001 and 2004, the main criteria that they came up with was there have to be very infrequent, essentially radiation events that could destroy like the atmosphere of a planet or, wipe out life on the surface of the planet. Um, the region of the galaxy has to have an adequate amount of metals in that, in that solar nebula, and we'll talk about what that means. And they're also and it has to be stable enough for a long enough period of time where Earth-like life can evolve. So perhaps creatures like us could evolve. Okay, so let's talk about that for a second. Okay, so these zone constraints. So when we talk about supernova, so when a supernova happens, it's basically when a very massive star reaches the end of its life cycle, the core collapses and then the outer envelopes just kind of explode outward. And so it's a very violent explosion that that produces a lot of high energy particles that can go out into the interstellar medium and like energize a large volume around it. And so uh, the regions that tend to have or that used to have the most amount of supernovae was actually in the bulge of the galaxy, so that the bulge region of the galaxy, because there are a lot of stars there, and the star formation happened very very quickly and very early on. And so you end up with a lot of frequency. End up with a frequent amount of supernovae in the bulge of the galaxy. So that's one region where you wouldn't expect to find um, uh, really a habitable zone for Earth-like life. The next region that where you can end up with supernovae is actually in the spiral arms of the galaxy. So the Milky Way has obviously these pinwheel-like arms that like emanate from the center of the galaxy and kind of spiral outwards. And within these spiral arms is where you have a lot of star formation. And when you have a lot of star formation, you also end up with a lot of large massive stars, which then can become supernovas as well. All right, so let's talk about how these spiral arms are actually formed and how they're maintained. Okay, and this is done by an idea called a density wave. Okay, so if you're driving on the freeway, you actually encounter density waves kind of pretty often. So what you're seeing here is a traffic camera, and as you watch the traffic on the freeway going away from us, you can actually see there's a traffic jam that kind of propagates through along the highway in the opposite direction as all the traffic is flowing. Okay, and that's actually a density wave. So you have the material, which is all the cars moving on the road away from us. There's a material speed where all the cars are moving away, but you see that traffic jam moving backwards through the material, and that's actually a dense region that's propagating through the material, and so that's actually a density wave. And so the same thing happens in galaxies and in the spiral arms of galaxies. Those spiral arms are actually density waves moving through a disk of material. Okay. So if we look at this person named Kevin Pluck actually generated a very simple animation that explains it pretty well. And so what you have here is you just have a disk of, for instance, stars or gas clouds, um, just orbiting around in a circle at different distances from the center. But the orbits are slightly slower as you get further and further out. So it's basically called differential rotation, where the particles on the outer track are actually moving slower than the particles on the inner track, right? So it's not rotating like a record, it's actually rotating what's known as differentially. And so what you do is you actually elongate those orbits into ellipses, and then you rotate those ellipses. And just by doing that, you can actually create these density waves that you see here. So these particles are still all orbiting at the same velocities around the center of the galaxy. It's just now their orbits are slightly offset from each other. And by doing that, you end up with these gas clouds now entering and leaving these regions of high density where all these gas clouds kind of bunch up together. And when that happens, those are where the density waves are. So you have material moving into and out of these dense regions. Okay, so what's happening inside those density waves? Okay, so when a gas cloud enters one of those dense regions, these gas clouds are very massive and very, very large, and so these gas clouds will actually collide with each other, and they'll compress, and by compressing, they'll then form stars, and so you end up with very massive stars, and you end up with like low mass stars, and stars in between, and so on. So you end up with stars of all different types of masses, and the very high mass stars are gonna burn very, very hot, very, very quickly, and they're gonna look very blue. The low mass stars aren't going to be quite as bright. They're not going to be as hot. They're going to look redder, and they're also going to last a lot longer. Okay, so both of those types of stars are born at the same time in the same region, and because the high mass stars are so bright, they basically outshine the low mass stars. So when you look at spiral arms in galaxies, the reason why they look kind of bluish white is because the blue newly formed stars are outshining all the older red stars. And so as the gas cloud comes in on one side, so for instance in this image here, as it comes in from the top, you get all these stars forming, and as the stars kind of slowly pass their way through the spiral arms over, you know, hundreds of thousands or maybe, well, I would say millions, but let's say thousands to hundreds of thousands of years, the very high mass stars will then, become novae or supernovae, and then uh, redisperse all their material back into the interstellar medium. So, you'll end up with gas and dust and, all the stuff that made up the star to begin with dispersed back into space. But the old stars will be left behind, and those will just continue on. And because they're not so bright, as they travel to the rarer regions, so out of the dense regions, you tend not to see them as well. And so that's why it actually looks like there's just empty space between the spiral arms. Okay, so if you spend a lot of time in spiral arms, so for instance, if the sun and the earth spent a lot of time in spiral arms, you get a lot of star formation. Okay, so what we want to do is we want to look for stars that don't spend a lot of time in spiral arms. So basically, they don't pass through these density waves very often. Okay. And so like when I talked about the traffic, there's a material speed, so the car's moving, and there's a pattern speed where the wave actually moves. Okay. And so in the animation that I showed you, so this animation here, in this case, the pattern speed doesn't move. You only really see the material speed. Okay. Oh, it's not playing. Okay. Well, anyway, but if you imagine those elliptical orbits actually moving as well, uh, also rotating as well, so slowly rotating as the material moves into and out of the dense regions, then you end up with a pattern speed of the spiral arms as well. So if the material speed and the pattern speed are equal, and you're not in the spiral arms, then you're at a region called co-rotation, where the two velocities match. And so if you're basically a star between spiral arms at co-rotation, you won't spend a lot of time passing into these spiral arms, passing through these spiral arms. So you really don't aren't won't be affected by uh, you really won't be affected.
Okay.
This one is getting nice and juicy. Very interesting presentation.
I wonder if I can run this presentation for him. Yeah, maybe I should try to run it for him because I've got a Mac here. Stand by, everybody.
Sorry, folks. Yeah, this computer is just does not want to run it.
All right, I'm joining right now, folks.
Okay.
If you'll bear with us, sorry about that. Those of you on the video call, I can probably edit this down, but those of you live, you know. Okay, just 1 second. I'm getting on Zoom right now. All right. Give me just one more second. Okay, everybody. Okay, let's hold on 1 second.
They have an echo on you.
You able to load it?
It's telling me I don't have permission.
Oh,
Can you share it with ihewitt@coastal.edu?
yeah.
That should kill the echo.
Sending. ihewitt@coastal.edu.
Yes, sir. Oh, wait, here it came in. Verifying link. Loading presentation. That's a good sign. It's making me jump through several hoops.
Okay.
There we go. Now, how are we supposed to? Yeah. Sorry, it's got the Microsoft thing where it's doing tons of pop-ups.
No.
We'll try opening it locally.
Okay.
Yeah, give me one more second. Folks, sorry, I'm getting lots of all right, let me try to get to this to full screen here and then should be in good shape. If I can share my screen, folks. No, it's a Zoom thing, permission.
No.
Um, to change the permissions, you have to get out.
Oh,
I'll be right back. Um, sorry, folks. Again, I apologize.
well,
This
I
should
guess in
do
the
it.
meantime, if anybody wants to talk astronomy, you guys have questions so far? Ooh.
It's about best we're gonna get for right now. Sorry, you'll have to see my little bar at the bottom. Uh,
Wow. Oh.
is this where you were?
Um, Actually, if you can just go to the Kevin Pluck animation, I think maybe we'll just start from there. The next one,
Or
I think. Yeah.
oh, did I miss it?
Yeah, it was further back. Right there.
Um,
Yep, right
sorry.
there.
Turn it back to you, sir.
Okay. So yeah, I apologize about that. So I don't know where I got cut off, but let me just say that okay. Basically, the way spiral arms are formed is by orbits intersecting themselves. So you imagine circular orbits being stretched into ellipses. Those ellipses being slightly offset from each other, and then all of a sudden you get these spiral arms. But now, if you imagine, so in this case, in this animation, these ellipses are now fixed, right? And so the material is moving into and out of these denser regions that create these spiral arms that you see. But now, if you imagine all of these elliptical orbits actually rotating as well, then that spiral structure will actually rotate in the image that you see there. So that spiral structure has now a pattern speed. So that spiral pattern has a rotational speed. And the material is moving into and out of that pattern as well. Okay. So, uh, and because the material has a differential rotation, where the further out you go from the center, the slower the material is actually orbiting. And the pattern, the ellipses themselves are all basically kind of rotating as a rigid object. At some point, the material speed and the pattern speed are going to be the same. So at some point, some of those little dots will just kind of hover between those spiral arms or spend a lot of time between spiral arms. And that's basically the region that's of interest because those stars won't spend a lot of time in those spiral arms. They won't pass into and out of spiral arms frequently, and because that's where you end up with a lot of supernova events and potentially a lot of radiation. So looking for stars near the co-rotation distance from the center of the galaxy, that could actually be important as well. Okay, so Ian, if you could go to the next slide. So this is the again, this is the image showing you how star formation basically works. Gas cloud enters the density wave region. It compresses, forms stars. Those stars evolve. The more massive stars evolve faster, burn out quicker, and potentially become supernovas. And the lower mass stars just kind of make their way through and just kind of continue on with their life. So it's in those dense regions is where you could potentially end up with supernovas, which is potentially hazardous to Earth-like planets. Okay, so now if you move on to the next slide, please. Okay, so the infrequent supernovae. So basically, you don't want to spend a lot of time in arms, and you don't want to be in the center of the galaxy. Those are the regions where you find supernovas. Okay, so now we're talking about adequate metallicity. So when astronomers talk about metallicity, they talk about everything on the periodic table that's not hydrogen and helium. We call everything else metals. So the two most common elements in the universe are hydrogen and helium, and everything else is what we dub as a metal. And so what we need in order to form an Earth-like planet or a terrestrial planet, is we need a large amount of metals. We need a certain amount of metals to exist. So if there are regions in the galaxy that are metal poor, then you won't end up with terrestrial planets. You'll end up with a lot of like Jupiter-like planets, a lot of planets made out of hydrogen and helium. So you can't be, so you need to be in a region where the metallicity is high, but then you also can't be in a region where the metallicity is too high. So astronomers have found that in very metal-rich regions, you also end up with something known as hot Jupiters. So Ian, if you go to the next slide, I believe. So these hot Jupiters are basically just like as the name sounds, they're basically Jupiter-like planets, right? So very massive gaseous planets, but they're incredibly hot. The reason why they're hot is because they're orbiting very, very close to the star. And so these Jupiter-like planets can't form close to the star. So what we think is happening is you start out with a solar system that perhaps looks like our solar system with terrestrial planets in the inner parts, and then Jovian planets in the outer parts. So these gas giants in the outer parts of the solar system. But for some reason, these metal-rich solar systems, these Jupiter-like planets, basically migrate inward toward the star. And by doing that, because they're so massive and their migration inward, they actually disrupt the orbits of all the terrestrial planets on the inner part of the solar system and actually like kick them out or cause them to fall into the star. So that's actually going to be bad for Earth-like planets as well. So we can't have stars or stellar regions that are too metal poor, and we also can't have stellar regions that are too metal rich. If they're too metal poor, you won't form terrestrial planets, and if they're too metal rich, you end up with hot Jupiters that then kick all those planets out. So you have to be somewhere in between with that as well. So Ian, if you go to the next slide. And so again, if we look at our little diagram, what we see is that the metallicity in the Milky Way decreases as you move out of the plane of the disk. Okay, and it decreases very rapidly as you move out of the plane of the disk. So the thin disk has the most metallicity, and as you go to the thick disk, it has less. And then if you go into the halo, it's far less. And so it drops off very, very quickly. So really, we can only look for planets, terrestrial planets within the thin disk, within that light blue region that you see there. But also, as you move away from the center of the bulge toward the outer reaches of the galaxy, the metallicity decreases in that direction as well. So you start out with high metallicity in the bulge, but then as you get to the outer regions of the disk, the metallicity is very, very low. So there's a region in between there that's going to be our Goldilocks zone as well. So Ian, if you go to the next slide. And so again, this is the same image, only with the with the actual photograph of the galaxy as well. But so finally, we also need time for complex life to evolve, and so that's important as well. So when we look at life on Earth, the solar system is about 4.5 billion years old, and what we see is that as soon as the solar system forms, shortly thereafter, we get the first evidence for life forming shortly after the solar system itself formed. And so if we if that is common, if that's how long it takes for life to evolve, let's say about 4 billion years plus or minus a billion years, then maybe that's, I mean, if that's how long it took for Earth-like life to evolve on our planet, maybe that's just the way it is. Maybe it takes 4 plus or minus 1 billion years for life to evolve. So we have to give life enough time to become significantly complex so that way you end up with like humans or things that could potentially communicate with radio signals or something like that. So we have to give it about 4 billion years as well. So we need enough time for this to happen as well. Okay, so Ian, if you go to the next slide, please. Okay, so this diagram basically takes all those concepts and puts them together. And this was published by, let me see, I can't remember now, but basically this is in a published paper from 2004. I think it's Lineweaver. And so what you're seeing here, so on the y-axis is basically time, and on the x-axis is distance from the center of the galaxy. So on the x-axis, the far left side is the center of the galaxy, and the far right side is the very far outer reaches of the galaxy. And on the y-axis, the bottom is when the galaxy formed, and the top is the present. Okay, so about 12 billion years ago, or 11 or 12 billion years ago, is at the bottom, and present time is now. Okay, and so if we just look along the y-axis at less than about 5 kiloparsecs, so like if we look in the bulge region, and as you look through time, right? If you look from the bottom to the top, you can see that the bulge region there, in the beginning, there are just far too many supernovas for Earth-like planets to evolve, because it's so dense. It's so I won't. Well, let's not say really dense, but it's really tightly packed with stars, and a lot of stars of different masses. And so all those stars, all those blue stars, those hot, massive blue stars, are basically going to burn out and form supernovas early on. But those supernovas actually enrich the material as well and create a metal-rich environment, which then produces those hot Jupiters. So basically, within about 5 kiloparsecs from the center, so about so like 15,000 light years from the center of the galaxy, it's basically it's no good within that entire region, just because it's either too many supernovas, too much radiation, or it's too metal-rich, and those terrestrial planets will just get kicked out. And now if we look at the far outer reaches of the galaxy, so if we look at about like 15 kiloparsecs, that's the outer edge of the disk, there hasn't been enough enrichment. So there hasn't been enough supernovas to actually enrich the environment to create the metals that we need to form terrestrial planets. And so if you go from the bottom to the top at about 15 kiloparsecs, you can see that in the beginning it's just too metal poor, but then as time goes on, it's starting to get enriched until you get to about present day, but there's just not enough time for life to evolve, so that it just wasn't metal rich enough for life to evolve. But now if you look at where the sun is, so at about 8.5 kiloparsecs, which is about halfway out from the center of the galaxy, that's where the point of the sun is. That's basically where the sun formed. And so you can see that basically it's in a kind of metal-rich environment, and there is enough time for life to evolve there. So basically that green region is the region that we want to be looking for in the Milky Way. And you can see that ranges from about, let's say, 5 to 10 kiloparsecs from the center of the galaxy. Okay, so if you go to the next slide, please, Ian. And so this is what people initially thought was the habitable zone of the Milky Way. So you can't be too close to the center, and you can't be too far out. And this is also seems to correspond. So the sun actually seems to be in a region known as the co-rotation radius as well. So this is the sun actually kind of hovers between two major spiral arms, and we don't spend a lot of time in that spiral arm region. My screen froze. Still there?
We still hear and see you. But you can hear us, can you? I believe he is frozen. Boy, today it's just been a day, folks. a real Monday kind of meeting. See myself twice. Check my phone, folks, and you're on mute, sir.
Sorry about that. I now blame my operating system.
It's a real Monday kind of meeting.
Yeah.
Yeah, so this is not a good thing for Ubuntu 2404.
No, I don't think so.
Carry on, sir.
Yeah, so basically I'm at the end here, but so basically what the gist of this is that we can't be too close. We don't want to look too close to the center of the galaxy. We don't want to look too close to the edge of the galaxy. The center has too many supernovas. It's too metal rich. The outer edge of the galaxy is too metal poor. We want to look in the disk of the in the thin disk of the galaxy. We don't want to look in the thick disk or the halo. And the sun itself seems to be in a preferential location. We are at essentially the co-rotation radius, which is the region where the material speed and the pattern speed is more or less equal. So we don't spend a lot of time in spiral arms. The sun itself kind of hovers between two major spiral arms and doesn't spend a lot of time passing through these density wave regions. And so these initial authors, they basically said the good region where we should be looking is between 23,000 and 30,000 light years from the center of the galaxy. So this green annulus that you see in this figure here. Now, again, like I said, this was all, these are just from two papers, the initial two papers that put this together. In the meantime, like even in 16 years beyond that, so up to about 2016, a number of papers have been published since then. And if you look at those, basically the habitable zone of the galaxy is kind of all over the ice. Um, at least two of the papers have said that the habitable zone is actually within the bulge of the galaxy, within about 2.5 kiloparsecs of the center. Two other papers have said two or three other papers have said that the entire disk is habitable. Um, Two papers have said, again, that there's a habitable zone in this annulus that you see here. And a couple other papers have also said that the outer parts of the galaxy are habitable. So really, we have no idea. I mean, this is all very hypothetical because we really don't know what it takes for life to evolve. We don't know. We don't know the circumstances that are necessary for Earth-like planets to evolve, and we don't know really how detrimental things are. Um, we don't know how detrimental, for instance, supernova events really would be on a planet. Could life recover quickly from, a nearby supernova event, or would it be completely exterminated? I mean, we just don't know the answers to these things. So a lot of it is hypothetical. But it is a good starting point to think about these things in order to kind of and narrow down regions we should be looking at, and also to get you thinking about, what is necessary for life to exist on a larger scale, on a grand scale, like in the galaxy itself. Like, does location of the galaxy make a difference or not? And it's worth thinking about it as well, in my opinion. And so I'll just leave it there. I mean, that's really about it that's really my last slide. Um, but yeah, I apologize for the constant cutting out, but if you guys have questions, I'd be happy to answer them.
Okay, so beautiful. I have a question.
Sure.
Okay, it's nice to see all the beautiful stars and galaxy at night. And I have a soccer game at Woodson High School this Saturday. It's in Fairfax. And my game times are 9 and 11. And you guys can come watch my game on Saturday.
Okay.
Okay, yeah. So I don't think anybody's very close to there, so we're not close to there. Does anybody else have any other questions?
Can you send me a copy of your book?
The talk, we can do that. Yeah.
Like, you can send me a copy of the book. I can give you my home address.
Well, this is a talk. I mean, if we could email it to you.
Okay, you want my email address?
I believe Ian has it.
He has my email.
If you used it to log into the Zoom, yes.
Okay. I know my email is manishopa11@yahoo.com.
Okay.
Okay. Does anybody else have any questions? All right, we ran a little longer tonight. So if nobody has any questions, I'm going to go ahead and stop the live stream. Thank everybody who is watching. Let's see.